Everyone. So, this lecture is going to be on Stack 13.3 to 13.4 up here. And we're going to start off in 13.3 on counters. So please make sure if you want, you can read through the book on counters before watching this to get Daniel Steck's perspective, and then I have my own perspective on it. Um, so counters are what are counters? It counts, right? So the name. So if you have a device in your on your breadboard or your computer or whatever, right? In your electronics in general, right? It can count up 1, 2, 3, 4, 5. And you might think, wait, so what is that useful for? So if you were running an experiment, for example, and you have a detector that maybe if a particle passed through, maybe a muon, whatever it is, right? You can detect that and you can count how many muon passes through your detector per second, and then so you can make some measurements with that. But there's also another way to do this. A counter is also a way for a electronic system to keep track of time. So same experiment, a muon passing through a detector, but instead of passing through, right, it decays inside your detector. So the mean lifetime of a muon is 2.2 microseconds. So what happened is that, so if you have a little detector here, right, and then your muon comes in here, it gets slowed down, and the muon is just sitting here. And so on average, okay, the mean, it will actually decay into an electron and 3 neutrinos. I guess this will be a bar. Um, if you don't know what these particles are, don't worry about it. But the most important thing is that, right, this is 2.2 microseconds. Okay, there's a tau there. Okay, so what you would think is that, well, when the muon pass go in here, right, you may see a little pulse of light. Okay, but then when this decay happens, you will never see the neutrinos directly. Well, 10 to the minus 40 something probability of seeing those neutrinos. I just didn't want to be inaccurate in that. But this electron also creates a little pulse. Okay, right. So if you combine these two together, what happens is that you'll see a pulse for the muon and then another pulse for the electron. Okay, and this time between them is the decay time on average. Okay, so so what you can do is that you can measure. Oh well, if I see this muon coming, then I can start a counter, count 1, 2, 3, 4, 5, 6, 7, 8, 9, in maybe nanoseconds or, a fraction of a microseconds. And then you can count, oh, when you see the second pulse, then you can actually measure the lifetime of a muon that's passing through your detector, which is very neat. Okay, so that's another science application. And hopefully I don't have to tell you about why clocks are important in your computer. So, you want to keep track of time. You want to keep track of how long processes take. Um, um, Counting is also, I think it also, like your operating system also keep track of like the amount of resources that it uses. So being able to count up how much is just used is also useful. But so more physics application, and then you have computer engineering applications also. But it's applications everywhere. So like you know we as human beings also count, right? So we have counters in our head. Um, but this is different. The counter is different from what we learned so far, which are the adders, multiplier, multiplexer, which remember are all dependent on this combinatoric logic, right? And the idea is that, oh, you have some input, you put those input together in some logic gates, right? And then the output comes out. And this is always happening. Basically, whenever you change the input, the output comes out, almost instantaneously, basically approximately at the speed of light between on these wires, right? So the combinatoric logic, right, is very useful and extremely fast, right? This happens at basically the speed of electrical signal going through your device, typically on the orders of nanoseconds. Okay. However, right, the combinatorial logic does not allow you to store information to be used in the next calculation. Okay. And this is where sequential logic comes in, which is what a counter is. Okay. So in sequential logic, what happens is that you have to have a clock, or you can call it a clock, you can call it whatever you want. It's a pulse that indicates, oh, step, step, step. It's kind of a step iterator. Okay. And this is where we're going to construct some edge trigger flip-flops. So in the lab, you'll get to build some of these. And we see that, the read and write only happens, right, when the clock cycles either up or down. The drawing in this case is a down edge, so it means a negative edge triggered flip-flop. Okay. So let's see how this works. Okay. And this is a ripple. It's called ripple counter, because hopefully you'll see that, oh, the information just kind of ripples through your counter as time goes along. Okay. So the construction, erase all this stuff again. The construction is that, well, you have some D-type flip-flop, right, that takes an input of a clock, and it can also take data in. Okay. Remember, this data actually goes into two gates, one for R and one for S, but then the S is inverted compared to the R. Okay. Okay. And it has two outputs, Q and Q bars, and they're always going to be opposite of each other, right? Okay. So the weird thing is that basically this output here, the Q bar output, gets mapped to the input. So there's no external input except for the clock. Okay, so once you connect this to clock, what's going to happen is that hopefully the information, the bits in this ripple counter will just count up by itself, so you don't have to like do anything to it. Okay, and the output, the Q output, the non-inverted output, okay, goes to the next clock. Okay, so the clock only gets connected to your first count, your first D flip-flop. The rest does not. Okay, and this architecture is replicated over and over and over again, and this can keep going to others. Okay, so this is a 3-bit. You can have 4, 5, 6, 7, 64-bit counter, which will count if you're counting even like one clock. Even if your clock is 100 megahertz, it'll probably take many years. I don't want to do that. It was whatever 2 to the 64 is. Okay, whatever that number is. Okay, so let's see what happens. Okay, with this ripple counter, and then we're just going to do up to 3. Okay, so here, oops, here, right, this in here is the clock here, right? Okay, and then 2 to the 0, 2 to the 1, 2 to the 2. Those are the bits that are coming out. We can even call these like Q0, Q1, Q2 if you want. Okay. Okay. So, and then I'll repeat these labels down here. Q2. Okay. So what happened is that, right, as when the clock pulses in, oops, don't do that. Yeah. Sensing my touch. Okay. Okay. When the clock pulses in, what happened is that nothing happens until the clock goes to a down edge. Okay, so what happens to a down edge? Okay, what happened is that the data, which is whatever Q bar is, and then if we initialize Q0 at 0, Q bar has to be the complement of that. Therefore, Q bar is going to be 1. Okay, so Q bar is equal to 1. That means D is also equal to 1. So when the clock signal goes down, when you see the negative edge, the D gets sent over to Q, right? Right. The transfer happens when the clock pulses down, okay, in this case, and therefore now Q ramps up to 1. And then nothing happens to the rest of the counters because there's no clocks connected to them, right? But, right, when this goes to 1, right, the Q bar goes to 0, right, because they always have to be opposite of each other, okay? And that means, right, you have now 2 to the 1 power here. And what I did is I tried to line these guys up, yeah, where, right, now the binary value is going to be 1, 1, 0, 0. Okay, so this is the binary value, right? So this is 1, this is 0, this is 0. I'm just lining them up. Okay, right? And then nothing happens once again. When the clock pulses back up again, you have a positive edge. So this particular flip-flop doesn't care about that. And then I wait till the next negative edge. Okay, so what happened is that when the next negative edge goes down, right, now Q bar is 0, and that's connected to D, right? So what happened is that that data is going to get transferred over. So the next step is that it's going to change Q to 0, right? The first Q goes to 0 here, right? This happens, right, in this line. Okay, but not only that, right, but now, right, this 1 going from 1 to 0 is a negative edge, right? Because going from high to low is a negative edge. And now the second D flip-flop senses that, right? Because it's a negative edge trigger flip-flop. So when that happens, right? So once again, I'm going to rewrite this, right? You initialize it to Q at 0, and this was at 1, right? Now D is 1 at the start. And what happened is that when this pulse, this first Q, right, goes from 1 to 0, it's as if it's acting as a clock that's a negative edge, and therefore now D gets sent from in the flip-flop to Q, to its output, and therefore the second flip-flop goes high. Okay, so you get 0. Yeah, let me erase that a little bit so it's a little bit easier to read. 0, 1, and nothing happens to the third flip-flop. Okay, and now you get 0, 1, 0. Okay, which is equivalent to 2 in binary, right? Okay, so you start at 1, so the total value, well, you start at 0, the total value is 2, second value is 2, first value is, second value is 1, the third value is 2. Okay, hopefully you're going to start to see the pattern here. Okay, nothing happens until once again the next negative edge of the clock. Okay, the next negative edge of the clock, right, now it pulses down. Now it's sending that 1 that was stored in Q bar, right, forward to Q, and then also flips Q bar to 0 again. It flips the Q bar from 1 to 0. 0 to 1. Therefore, it's actually a positive edge, so it doesn't do anything to the second flip-flop. Okay. All right. So after the second down, the third down edge, 1, 2, 3, right? Nothing happens to the second flip-flop, so that stays as 1. But then, right, the first flip-flop went up to 1, right? Because Q bar used to be 1, that's connected to D, and D gets forwarded to Q, and then and so on. Okay, nothing happens to the third flip-flop, and now you have 1, 1, 0, which is 3. Okay, and then another edge comes, and we're going to keep going on this. Okay, what happened in this case is that since you start at 1, it's going to go down to 0, and that sends a trigger to the next, it sends a clock to the next flip-flop, which makes that also from, it just switches state, right? If it's 1, it'll go to 0. If it's 0, it goes to 1. Okay, and therefore the second flip-flop also goes to 0, 0, 0. But then when you go from 1 to 0, the output of the third flip-flop went from high to low. That's a negative edge, right? And what happened is that flips the state of Q on the third flip-flop to 1. Okay, and 2 to the 2 power, of course, it's going to be 4. Okay, and then now we're starting to see the pattern. If you keep going, then you get 5, 6, 7, 8, 9, and so on like that. Okay. So hopefully that makes sense. Um, and the idea is that you're moving this one clock, right? That clock signal being high from one counter to another, rippling along the number of counters that you have. Okay, that's why it's called ripple counter. So so it counts up at the rate of whatever clock signal you put into it, which is very neat. Okay. Um, so in FPGA, this is used so often is actually, you know, made into more of a program-like index, which is what this plus key is. Okay, the plus key, this plus number symbol actually represents the circuit. Okay, and whenever you guys, not even on a circuit board or an FPGA, when you're doing programming in like software, this is actually what's happening in your memory. Is literally that plus key is constructing a counter that you can count up. Okay. Um, so, and then I'm going to have you guys build this also in using Verilog, but using D flip-flop gates, but made out of NANDs instead. Okay, instead of just using these. So that way you guys see where these counters come from, because this counter declaration, right? There's a lot behind that. Okay, so this is basic. This is going to be the same thing as, you know, I guess that's 8 of these chained together. Okay. Okay. So whenever you see a little line of, a little symbol like a plus, there's a lot that went into that plus symbol. Okay. All right. Okay. So that's how a counter works in electronics, and these counters are the basis of, all the computation that we're doing these days. Okay. Next, I want to talk about a little bit about memories and registers. You can This is going to look similar. So once again, it's another type of sequential logic, where if you're want to remember stuff, okay, you need to be able to hold on to data that you input, wherever it comes from. Okay. And this is where a register comes in. So this is the reason why in those, you already started using it in Verilog, right? Whenever you define something that has a memory, you have to define it. So this will be a 3-bit, right? Let's say let's call this. Oh well, I don't like the letter O, but I'll put a little O with a little hat on it, so we know it's an O. Okay, that's why it's called reg. The reg here stands for a register, and this is basically just a memory bank. So in this case, right, the clock, the book choose to flip these around just to keep us on our feet, right? They chose to use a positive edge trigger D flip-flop instead of negative. That's fine. Okay. And this clock is actually connected to every flip-flop the same way. Okay. So the memory can only change when the clock goes from 0 to 1. Okay. Positive edge. Okay. And the inputs, right, are connected directly to D here, right? So whenever the clock pulls from low to high, whatever I0 is gets sent to O0, okay? And that's way these O's are all going to get synchronized together. This is similar to what yours guys already did in the lab, okay? And the same thing happens to O1, O2, right? And then O3, O4. And that way, whatever the input I is, they can come in plus or minus the clock cycle within the time period of the clock cycle. And then all the O's will be synchronized at the same time, so that when whatever process you're going to do with it, like let's say you want to add them together, multiply them together, right, shift them around, you can do whatever you want. All those O's are from the same cycle of computation. That way they're all in sync with each other. Okay. And you already kind of been seeing this, where let's say I made a 3-bit registry here, so 20 output, right? I'm just going to put output there. And then I made the input with a capital I, so don't use the lowercase I, because that's a special key in Verilog, right? And I map these to the switches, let's say, okay? So you give it a little positive edge, right? Like this. And basically, this registration happens when you do a non-blocking assignment operation, which is what this little caret equal sign means from the input to the output. Okay, right, and that's just a regular register. You can have shift registers. Okay, so register just remembers, synchronizes whatever your input is, and then remembers it for that one clock cycle. Okay. You can have a shift register, which is a slightly different operation. What a shift register does, oh, let's see what this circuit is. Okay, if you still have a positive edge, the clocks are still connected to all the clocks inputs for these D flip-flops. But instead of each of the Ds, right, having their own inputs from I0, I1, I2, the Ds are connected to the outputs of the previous flip-flop. Okay, so this hopefully will remind you of the counter, which is connected slightly different, right? But you are interconnecting these D flip-flops together to have an effect, right? And what is this effect? Okay, so let's say we started with, this input at the first flip-flop, and we're going to call that serial in. Okay, and we're going to see why this is going to be serial. Okay, and then we'll initialize everything at 0. Okay, this 0, this is 0, output here is 0. Okay, what happened is that when the clock pulses up, right, the input D, right, from the first flip-flop gets sent to Q. Okay, so now, right, O0 is going to get changed to 1, but since these clocks are synchronized with each other, right, what happened is that the second and the third flip-flop, they all send their data at the same time. Okay, and that same time means that, well, before this 1 gets there, the 0 gets sent forward, and then the 0 gets forward. Okay, so basically what happened is that O0 is going to change to 1, but then O1 and O2 stays the same, because the data that they had already tell them that, oh, I'm sending 0. Okay, so I'm going to write the second clock cycle in 1 in blue. Okay, and let's say we just have a 0 coming in after this. Okay, so now, right, the first clock cycle, we had 1, 0, 0. So let's write this down on the side. 1, 0, 0. Wait, how many zeros I got? 1, 2, 3, 4. Yeah. Okay. The second clock cycle, right? We have a 0. Let's just have a 0 coming in. We're gonna keep track of it one more time, and then this goes over. So you notice that the 1 basically moved from the first bit to the second bit. Okay. Let's do that one more time, just for sake of completeness. Okay, the third clock cycle, well, this started off at 0, it's going to send a 0 over. This started off as 1, it's going to send a 1 over. This started off as 0, it's going to send a 0 over once again. Okay, and so now the third state, right, let's do that in green. Let's just keep the third input as 0 also. So these are just numbers that are coming in constantly. Okay, okay, and then so this 1, right, this 0 gets forwarded to here, so nothing happens, so it goes to 0. Okay, so it goes from 1 to 0, and then this 1 gets sent over to here, which turned that 0 to 1, and then this 0 here gets forwarded here, which turns it into 1, into 0 still. Okay, so in the third clock cycle, you have 0, 0, 1, 0. You can see that this 1 is being kind of shifted over little by little, one bit at a time. Okay. Um, those of you who knows programming, this is known as a bit shift also. So this is a shift register. So why is this useful? So you have some serial, um, um, you have a list of data that's coming in, okay? And it's being placed in certain bits of your register depending on how many clock cycles it went in. So hopefully the name serial might have gave the name of the technology away anyway. So this is basically how your USB works. So the S in USB stands for serial, so universal serial bus. And then this is how your USB actually sends data out as one, well, sends data into devices. So it sends it one bit at a time, okay? And then the inside your computer or your phone or whatever, right? It has a serial to digital converter. So this is known as a SIPO, serial in, parallel out, meaning so this is serial going in, this is parallel going out, meaning all the output goes out at once. Okay, and this is how a lot of data are actually sent. Because right when you connect a cable with each other, you don't want to connect a cable with like 64 wires in it so you can send 64 bits at a time, right? You want to have a thin cable that are flexible and won't break. So you can send one bit at a time in a single cable, but then you send that really fast, so therefore you make up for the fact that you serialize the information. Okay. So if you look up, the technology of USB, when, well, this is USB 2.0 already. When USB 1.0 already is probably a lot slower. You can actually send about half a gigabits per second, so about 480 million bits per second. So this thing is pulsing up and down a lot, and it has actually two data interface. So it's actually doing two serial things at once. Okay. When USB 3.0 came out, they added more wires, so not just D plus and D minus, but also TX minus and then RX. So these are, T means it's the sending, and then RX is actually the receiver. So they have dedicated sendings and receiving ports in USB 3.0. And then when you have USB-C, which is what most of us use now, they have even more connections in them. Okay, so a lot of the technology of USB is based on this serial in, parallel out technology, and then they just make the wire, they just make put more and more wires into them, just so that we can have a higher throughput. And then now you can do 64 gigabits per second, and also there should be, yeah, up here, yeah, V bus. Those are the voltage bus, meaning they can carry I think up to 20 volts across, as opposed to just 3.3 volts, which was the other USBs. Okay. All right. Another thing that the shift registers are used for is to basically put serial data into a processor, right? And notice that one thing is that, let's draw this, right? Your processor, your FPGA, whatever it is, right? Right. You want to have a lot of data coming in, but then it only has limited number of connection that can handle. So therefore, you can actually send in. You have a serial to parallel converter right inside your processor, so that way when the data comes in one bit at a time, it can stack those together, and then now it can do this combinatoric process in there, right? Okay. Another interesting application that I didn't know about until I read it in the book is that your keyboard also sends a signal in serial. So when you type, 6 on your keyboard, for example, it sends out a certain pulse in a serial fashion. So it actually doesn't send like, one, wait, what's 6 in binary? It doesn't send 0, 1, 1, right, in 3 bits. It just sends a pulse, right, that represents 0, 1 1 in serial fashion. Okay, so as I mentioned, this is called serial in, parallel out. Oops, we can highlight. Okay, if you want to learn more about this, this website, allaboutcircuits.com, is a pretty cool resource on technology that we use every day. This isn't in the textbook, but I just want to mention it since you have serial in, parallel out. Of course, you can also have parallel out in, serial out. Okay, in this case, I just want to kind of sketch it schematically. You can look up more of this if you like. So this is the data that's coming in, DA, DB, DC, right? It's 4 bits of data. And what happened is that you have a similar construction as this, okay? But everything kind of goes backward because what you want to do is actually have the, have the data go out instead of going in. And I will have you guys think about how to build this in using the flip-flops, okay? And what happened is that the data can come in, but we don't actually worry about that, your construction here. But what you want to do is, let's say you have, let's just make up some data set here, 0, 1, 0, 0. So what you want to do for this data output here is to have it so that, so for the first clock cycle, right, that the first clock cycle that goes out to be low because you have a 0 there, the second clock cycle there to be low also, but then the third clock cycle, you want the data to come out high, and then the fourth one to be low. And that's what the data is going to represent, right? So it's going to represent 0, 0, 1, 0. And this is what the serial output of your USB port does, right? It needs to also output serially and then it can take in data serially. This is a parallel in, serial out device that you will have you guys work out in the pre-lab. All right, I think that's it. And thanks everyone. So, and then I will work on posting the next lecture or recording the next lecture in a second.